Thank you very much, John. So, this next talk is definitely going to be a little bit more on the technical side. I apologize in advance for that. And it is about this era column that we have in the Numerai data. If you are not in Numerai at the moment, or you are not interested to do so in the future, you can still get something out of it, because the advancement that I'm going to go into more detail was submitted to the paper was submitted to a journal that is not about finance at all. And the general principle is applied every time that you have a grouping feature or a looping mechanism in your data, which you cannot use in your live predictions because the observations simply do not show up in live. The era is just an increasing integer number that just goes up, and using that as a feature is a very, very bad idea, obviously. But it holds a lot of information. So it's the only grouping mechanism that we have in the Numerai data. Without, the era is just a giant 5 million times 2,500 matrix of integer values. But the era information actually gives us a lot of value that we can try to use. And I remember that, again, the journal that was accepting the paper used it on completely different data sets where a similar grouping exists. And I also remember a discussion on an issue tracker from somewhere, from somebody from a pharmaceutical company who wanted to use the same principle to group data from different patients together. Again, something that you cannot use, a feature that you could not use in your live predictions, but something that holds important information. So even if you are not into Numerai, I still hope that you can get something out of this. So my name is gBrecht in the tournament. I'm Bastian in real life. So gBrecht is short for my very German last name, which you can hardly pronounce. I come from the southwest of Germany, where I live with my wife and daughter. When you make the triangle of the core skills for the Numerai tournament, so finance, data science, and software engineering, I place myself far away from the finance side. I'm a general computer scientist by training, somewhere in the middle between the data science and the software engineering part, but again, very, very far away from the finance. And I am a certified decision tree hugger. The stuff that we're going to see now is exclusively the library and the things that is only for decision trees. It's what I understand, and all my models are decision tree ensembles. Yeah, let's leave it at that. I don't want to get too much way ahead of myself in the introduction already. I'm going to have two parts in that talk, and the first one is explaining a little bit it's called historical advancements or ideas in the field, and then going more into detail of the most recent advancement, which I hope holds the most value for you going forward. Yeah, and with that, we are jumping towards April in 2020, so around the time eventually starting the tournament, but I don't know if that's that's rather a coincidence, where the topic of era boosting was publicized by, it was actually the founder, Richard, who posted this in the forum. And the idea of era boosting is you have your training data X, well, I can't point here so well, but I have your training data X, and you define a number of boosting rounds. It doesn't need to be single trees, it can be batches of 10 trees, you can go crazy and say you want to start with 100 and then go down. But what you are going to do is you will train just normally on what you define as your current train errors, again starting with of course X, your whole data set. Then you do an in-sample evaluation of the whole training data, so always the whole X. And then you have an evaluation function that identifies the errors that your model is currently doing the worst in. And it's your judgment what the worst is. But then you are setting your next training errors to the worst errors of your current ensample performance, with the idea that you are forcing your training mechanism, your algorithm, to focus on the errors that you are currently doing worst on. So kind of like a focus training on where the biggest error or the worst performance is. I personally have never had success with this method, and I have never seen or heard anybody who was. If you do it, I want to tell, that's completely fine. But in my judgment as to why this is going to do with how the algorithm actually works. When you are training when you are doing your training in your machine, in your decision tree library, what it does is it selects the tree that will decrease the training loss the greatest. That's actually what is proven to, what these algorithms have been proven to do. And when you are doing your in-sample evaluation, of course you could do it again also on the training loss, but that would be just quote-unquote stupid, because you would be redoing what the algorithm can do very much better than you. So you will be evaluating on a metric that is not the training loss metric. And then you are setting your next training eras on something that has been having a worse performance based on a metric, but not on the training loss. But the next training in a decision tree ensemble algorithm is always based on the residual of your current ensemble. So where the loss of your current ensemble is worst. And that, I think, just doesn't add up when you are basically swapping the loss function for a metric. And that's why I think that era boosting is not going to cut it for you. We have the first question already.
Okay. Well, you sort of answered my question with the last thing you said there, because my question would be if like, why focus on the eras where you are really bad instead of actually targeting the focus to the eras where you're really good?
Okay. Keep that question in mind when I come to my funny moments towards the last third of my talk. My short answer is because Numerai is a game about trying not to be bad. That's my very short answer to this, in my personal opinion. But I will have a whole stand-up piece on that in the third quarter. Yeah, but that's my short answer. We fast forward a little bit, but not very much, to September of the same year, where somebody, MDO, posted this. I don't know if he was working with the team already at the time, but he's now the chief of research at Numerai, and he posted something about custom objectives. So custom objectives are basically, you have your big machine learning library, doesn't matter if it's LGVM or XGBoost, and you have this entry point where you can put in a custom objective function that will override the internal objective function that is being used for the training. And the way that you do this is that the signature of this function is fixed. You get the current predictions of your current model and the truth, the targets, and you have to return the gradient that can be used for the next iteration. And what they then do is they inject, that's why the syringe is there, they inject the information about the index of the eras into that function, use that to create the era-wise predictions and the era-wise truth, and then do all kinds of fancy differentiable PyTorch based or something else calculations that then come up with a loss. I'm putting here this spiral in because when you read through the forum post, they are deriving a very complex Numerai specific Sharpe ratio with cost functions in, so very, very sophisticated stuff. But again, I did not have the most success with this. I'm sure custom objectives are used with great success throughout the tournament. Again, if you are using them, please continue. And I'm sure that objective functions are a very, very great tool. It's just that it's very hard to plug in an objective function that functions well with the standard boosting algorithm that they have. To me, this always sounds like kind of dark magic when you want to actually get it to train. Oftentimes I plug something in and it just doesn't train. And even if I get something to train, it kind of seems like a pointless tournament because I know I have something to train. But of course, that's not the goal. The goal is to have something that actually works. And again, my personal judgment as to why, especially era-based custom objectives do not work so well is because they collapse about 5,000 of the rows into one single value. So when we do an era-wise loss, the training algorithm does not get 5,000 gradient values, one for each sample, but one for each era. And that is, in my opinion, a huge impact, huge deviation from the way that normally works. So, in my words, custom objective era-based functions are not separable in the sense that they give you a loss value for each of the samples, but for each era, and that is very hard to train. Again, fast forwarding about 2 years, when Numerai user Jeffrey the Wind, aka Timothy Lalise, entered a 1-year contract with Numerai, so he was a kind of intern there. And there were several results. You see the reference section here blowing up a little bit. There's a lot of material available on what we did there. One of the things is the idea of era splitting. Am I breathing too loud, or is that... Okay, yeah, it's good, yeah. Is the idea of era splitting. Era splitting is basically the core idea of the talk that I want to go more into more detail, but this is the version 1 of it. I will come to more later. So what he released there, what you can see here still on this GitHub, is a complete implementation based on the scikit-learn his gradient boosting regressor. So, and that is, as it is common with scikit-learn implementations, slow. Very, very slow. So much slow that you can hardly use it on the full Numerai data. You can, but yeah, no GPU, accelerated, very, very, very slow. And you have to install a complete fork of the scikit-learn library. You have a different namespace, so this is a really, really bloated library that you're doing there. The hyperparameters that you use to control what the algorithm actually does is several. They have funny names like gamma, blamma, vanna, and you can choose combinations that are the same. You can choose combinations that are pointless. You can choose combinations that actually do opposite of what you want to do. So it's really, really complicated. But the idea of era splitting was born already there in July of 20, or in that year when when Tim was doing an internship at Numerai. But before we go into more detail, what era splitting really is, a short intermission, which have actually nothing to do with eras at all. 2 years later, Numerai user called Murky, sometimes also Murky Automata, posted a single file, even a notebook I think, so probably not even software, but okay, to say that okay, with this class, with this booster class, you can train 200 trees per second on a A100, so on a Google Colab GPU on the full Numerai data set. And everyone was like, what? But this Murky had a track record. Colleagues mentioned earlier the true contribution rules. That guy was the one who said, well, I came up with a closed form for true contribution and just Numerai to give us the inverse Hessian of the optimizer and then we can solve it. And even the founder was like, dude, what? The same Murky, when you look at the last fireside chat, he was mentioned as, yeah, I can't imagine anybody is doing well without buying data on Numerai signals or crypto, and they used again Murky to say, yeah, there are some exceptions, but please don't count on people as smart as him. Or when you look at the Signal Alpha introduction blog post, his profile page is being screenshotted and saying exceptional users are always going to be exceptional. So not quite the normal average kind of Joe that you have there. And the stuff worked. I have not asked Tim and Pranju on the next slide if they were inspired by this, but the reason I'm including this here in this presentation is that it shows the power of a custom CUDA-based kernel implementation for a very dedicated task. When you have your machine learning or your gradient boosting libraries like GBN and XGBoost, they have been around for a long time, they are battle tested, but they are very big C-based libraries with bindings to multiple languages. They all have to copy the data to their internal data representation. So, yeah, they are very, very good, they are also fast, but stuff like this shows that you can do it more memory efficient, with at least the same speed, and with more extensibility, because here Murky just used with function declarations for just-in-time compilation for the GPU, and the rest was pure Python. So it was not even done in anything C or machine. So that really is why I include this here. And then we have what is going to be the main part of the talk, and that is Warp GBM. So on May 28th this year, again, Tim, together with Pranju Bahadur, who goes on Numerai by the name of Thralty, but he doesn't have a profile picture, so I uploaded his GitHub profile picture here. They released version 1.0 of Warp GBM, which is exactly that, a custom-written CUDA kernel-based decision tree gradient boosting library, written completely in Python and CUDA. It implements directional era splitting, and we'll go into more detail what that is and why that is maybe helpful in a few seconds. And it operates directly on the NumPy array you pass to it. So no need to copy your data. If it fits into your RAM when you load it from the Parquet file, you're good to go. Each one of those three aspects would be interesting enough for me to look at it, but it does all three. And when we now try to think, okay, how can we bring these era information closer to what the decision tree algorithm actually does, the core is to look at how the trees are actually constructed. And that is the way the nodes are being formed. The nodes are being formed in a way that all of the samples arrive at the node, and then one feature and one value is chosen to divide the samples into two parts. One part where the feature values of that sample are lower than the value chosen, and the other part where the sample values of that feature are a bit bigger than the value chosen. So it's a split. The data is split by the value of that feature. And as we have a lot of features and a lot of values, there is a lot of possible splits. And the splitting criterion defines which of the splits to choose. And that splitting criteria, which is on the screen at the moment, is the one taken from the original XGBoost paper. And I put myself, somewhat in the vicinity of the data science thing, but I cannot read that. It's a bunch of letters that have no meaning. So the only thing I can see here is that the three terms are actually almost the same. So let's just look on one of those terms. But still it's just letters that I have no idea what to do. So let's translate that into a form that humans can read. And this relation is simply that, what it says here on the slide. It's the sum of the gradients of the data divided by the sum of the second order gradients of the data. So again, we are looking at the split criterion here, and that basically says we want to choose the one where the gradients improve the most, but if your gradients improve by some higher level gradient stuff, we don't want that at all. To me, that's a genius idea that they are simply dividing out all the higher order gradients to say, look, I'm really, really greedy. I want you to be good now. If you're good later, go away. Again, in Numerai, we're treating the problem as a regression kind of thing, where normally most of the people, including myself, are doing a mean squared error kind of loss. And here the joke's completely on them, because the second order gradient for that function is simply a constant. So it's just, you can imagine a 1 being there in the divisor of that relation, so not relevant at all. But again, you can use it for classification, you can use it for different functions, and there it's actually, I think it's a great idea. Not come up by me or anybody else. Again, that's from the original XGBoost implementation. So bringing that back to the whole function, they are squaring the upper part of the equation to cancel out the signs of the gradient. And on top and the bottom here we have an addition of a realization penalty, and apparently I have learned that if you are doing this for the left part, so which are lower than the feature value, plus the right part minus everything, again apparently it favors even splits, so where the two sets which are being created are about equal size. I cannot prove that to you, apparently it is like that. Please don't ask me why they're taking half of it, doesn't make sense for me at all, would be no difference, but that's how they do it. This is then the splitting criterion. And now, what Tim and Pranshu came up with is the era splitting criterion. If you could not spot the difference, I could not either. And we can go again. This is the era splitting criterion, this is the normal one. I don't see a difference. The difference here is there is an additional index at the top, even here. And that simply says that the era splitting criterion is the exact same as the normal XGBoost based era splitting criterion, but done for each era separately and then averaged together. So they are computing what the best split is, not for the whole data set, but once for every era, and then they're doing the average. So you could say each era gets to vote on the best split. Or you could say that the split is chosen where there is the largest agreement across all of the eras that you're looking at. And the idea behind this is that the chosen split has the greatest decrease of impurity in the data over all of the eras that you're looking at. This creates one kind of complication, one kind of problem, and that is the direction of a split, which you probably have never heard of. I did not before I read that. Again, on the left-hand side you can see how a split is done. One feature with one value is chosen, and then left and right regarding what the value of that sample for that feature is. What is additionally important is, in a decision tree, any node holds a prediction value. So with any node you could stop training there and you would have a prediction value. And that prediction value is the mean of the samples which are in that node. So if we now say we have the first split and we come to the first, all of the data coming in here, it flows left and right. These nodes immediately have prediction values. It's just the average of all the samples which are going to be put in here. And they say that if this prediction value on the left-hand side is greater, then this is a left-sided split. The direction of the split is to the left, or if the other ways, the split is to the right. Every split has a direction. And this is, if you have one data set, not interesting at all, simply because the split is either to the left or to the right, but there's no consequence for it, because you only have one data set. But in the era-wise splitting criterion, where you define a split, or where you have a split which is relevant for each era, the direction of the split can be different for each of the eras. And that is, in the research that the colleagues did, the big problem, because it basically says that the eras are not in agreement whether or not the split should be to the left or to the right. And so they came up with the definition of the directional agreement of a split, which is simply the average of the direction across all the eras. So if a split is to the left, that's a -1. If a split is to the right, that's a +1. And if all of the splits going to the same direction, then your directional agreement is 1. If half of the splits go into one direction, so they are completely undecided, then directional agreement is 0. And the current warp GBM implementation says, of all the possible splits, before we are looking at the values of loss increase for the splits, we are masking out all the splits which do not have the maximum directional agreement. So directional agreement is actually much more important than the actual performance of the split. This goes back to a little bit to your first question. It is much more important to not do junk than to do the most wide step immediately possible. Again, in my opinion, that's what Numerai is about. Trying not to overfit, trying not to be stupid. It's very hard not to be stupid, apparently. So, by the way, this is not the actual implementation code. Tim would be rotating in, I think, Canada he's based. This is just some pseudo Python-like code that I wrote here to illustrate the idea. But again, the splits are masked for only the max direction once before even the impurity decrease is being looked at. Oh, so, wait, I put my microphone here. You're still here, so I had confidence in you making more questions, okay?
Sorry, when you say choose best split, what splits are you choosing between?
All the possible splits.
Oh, so it's the same as like what actually...
Same as, but it's basically when before we had only one entity voting on that, and that would be okay. This split decreases impurity by 5, this by 7, so we take the 7 split. Here we have now #era voters, and so we have to decide between a lot of options, but first we are kicking all of those out which don't agree to the maximum amount on that direction. That's the difference.
So at the start, you'd expect any split made to be basically moving all areas in the right direction, or as close to that as possible. Right, not based on the actual increase in trading models.
Exactly. I would put it like that. If we have two splits, one, all the eras agreed to go to the right, but with a really shite impurity decrease. We are still choosing that over the split with a huge impurity increase where one era says, no, it's a left.
Perfect, thank you.
You want it back or shall I park it here?
I can take it back. No, I'm just kidding.
Alright. This might be a very good point in time to show you how it actually works in the API. The only difference to your normal scikit-learn interface kind of thing is that you pass in a third parameter, and that is the era ID, where you basically group the samples that you're giving to the algorithm into the, and now comes my words, buckets that you want the algorithm to consider. Why do I call them buckets? Because these buckets do not necessarily need to be the same as our Numerai eras. We have 1,000 something Numerai eras at the moment. I think it's 1,100 already. That's a lot of different people to vote for a direction of the split. So it might be actually, how do I say this? Experimental research has shown that a good number of buckets to sort your eras in is much, much lower than the actual number of eras that we have. It's of course a non-solved ongoing topic, but what I want you to understand is that if we have one bucket where all the samples go in, that's the current implementation of XGBoost, LightGBM, what they're doing. That's one end of the spectrum. You're not doing era splitting at all because it's only one bucket. The other end of the extreme is that you create as many buckets as possible, which in the Numerai case is every era is their own bucket. That's why, I mean, it's called era ID, it's called era splitting, but ideally the Numerai word era is then something different than the, in my words, era buckets that you passed to the algorithm. And so, now the moment that, that I'm dreading most is the question, is it any good? And this is the point in time to sit you down for a very stern word of caution. Numerai does not call itself the hardest data science tournament in the world without a reason. Of course, it's a self-proclaimed marketing slogan, so probably 10 of the tournaments are saying that. But the reason that Numerai is hard is that when you are doing training, you define yourself what is good, and then you're trying to reach your own yardstick, buying yourself into overconfidence that what you are doing is actually good. And then, because everybody reserves the right to shoot themselves in the foot, you submit a model which is heavily overfit. If I may do a reference to the previous talk that I have never heard before, letting a machine take those decisions on when training is done, what features to engineer, what metric to evaluate to, has this major appeal to me that I am not tempted to be too greedy. Which has nothing to do with light coding, by the way, which is just taking my hands away from the important knobs and whistles. So instead of asking or trying to answer, is it good, I'm going to try to answer, what does it do? And there I have set up the following experiment. So we train on 922 eras. Valuation, if you tell me that. With a 16 era embargo. I choose to train only one tree, with the benefit for me that I do not need to care about learning rate and call sample by tree. So, because one tree, I of course give it all the feature, and of course there's no learning rate stuff to be done with only one tree. But of course, as Alex showed on the example model, normally we train G trees up to depth 5, which would be 32 values, which is a little bit low for our era-wise evaluation metrics, which are usually about 5,000 samples. So depth 12 gives them at least 4,000 something points to come out with. One, we are doing the most conservative extreme of not doing any era splitting at all, so putting everything in one era bucket. And on the right, as I said earlier, I'm putting it into 10 era buckets, not 1,000, so, well, 922 as I had here in the training data, but 10 era buckets. The resulting tree here, if we are giving it all to the algorithm without any constraint, it does 4,000 splits and uses 1,800 something of the features with a completely trivial by definition directional agreement of 1, because it's only one bucket. So let's just put that here because I wrote that there. If we force it to use only the max agreement split of those 10 buckets, it does only half the splits. It uses 500 features less. So immediately that's one major result for me in the sense of that this algorithm is getting much more conservative, or again in my words, is more cautious of doing dumb stuff. And now for the numbers. And I let you pick out your favorite one. With the exception of standard deviation, which is a little bit better on the other one, it's straight up worse. Every metric, even the risk ones, even the drawdown, is worse. So, when we have one tree, the greedy method of not limiting yourself works better. The mic, he gave the mic away there.
But it's just very short. How do you choose the euros going into a bucket? Is it random or is it the first 10, next 10?
Very good question. It is not random at all. You have to trust me that I did not train this towards this experiment, but that is something that I came up with through some experimentation. It's not random at all. But very, very good question. Very good observation. Now, this is not going to be the final one. I have one more level to go, and that is I redid then the experiment, not with one tree, but with 5. The non-directional splitting algorithm uses all the features. This uses more features, but still leaves 250 out, which you remember in the previous, it had 500 less than the left one. So about half of the amount of features that it was using less, it caught up to what the normal algorithm does. When we look at the splits, it's still the half relation. It's still 20,000 to 10,000. So it's still doing half of the splits that it would do if we were not constraining it by the direction. Directional agreement still trivially 1. And when we look at the numbers, we see now that the table has changed. Even standard deviation. So what I want you to take away from this is then that, as the gentleman asked already, the amount of what buckets or how to sort the eras into the buckets is a major, major question affecting how this thing works. If you compare what the example model does, I mean, basically the example model is trivially simple. It's actually just one hyperparameter saying use only 10% of the features for each tree. But then everybody is hunting for these non-linear feature combinations. How are you going to do that when you just have 10% of the features? So this call sample of 0.1 is a necessary, in my words, a necessary constraint that we have to do on the algorithm, otherwise it just goes batshit crazy. And here, we can do call sample, we can give it all the features, and it goes not immediately batshit crazy. So, for me, this is a very, very good thing, because I have not to be as cautious, not to overfit immediately. And of course, directional agreement, I now forced everything to have a directional agreement of 1. Maybe that's not optimal. Feature visualization was, I think, mentioned by you in the beginning. Everybody was feature visualizing full. Now it has kind of materialized that the optimal value, if you're using it, is somewhere around 0.5. Maybe that is also existing for the minimum directional agreement. Maybe it's a good thing that, I don't know, 10% of the buckets vote in a different direction, but I don't know that. And with that, thank you for your attention, and we are happy to take some questions.
When I saw the bidirectional agreement thing, I kind of saw that as a good way to check if you are overfitting. Because if you see it as still 1, then you're almost guaranteed not to be overfitting in a way.
Can I... No, I don't want to go through all the presentation again. I want to go through here again. The first thing I would rather look at is the number of splits and number of features used. Because there's no metric, no setting whatsoever stopping the algorithm from simply doing more splits and using more features. But he, she, it, they decide to not do it because of the loss, the split criterion that we have defined. So that's what I would look at first. But then, of course, the minimum directional agreement that you are willing to accept is the most, or is the strongest statement that you can give to the library.
Yeah, because, I mean, you know, this isn't that much better, but I would expect that this would need to be trained for a longer time. But...
Well, if you want to put your money on a payout chart of 0.4, then you're welcome to do that, but that's not what I was trying to do here. I was trying to, I mean, it's 5 trees, so the absolute values are not that good here.
Thank you.
So in the previous break I said that I was impressed with both the quantity and the depth of the questions, but that apparently has... Alex is rescuing it, okay.
Yes. I wanted to ask, when you did this experiment, if you did any kind of feature neutralization or not?
No, nothing at all. Nothing at all. And I specifically choose it that I could do call sample by tree 1, so I would have to take as little upfront decisions as possible. I don't want to influence the experiment, or I want to influence the experiment by the littlest way possible. Oh, he's here.
Yeah, so I'm not a tree person, so a couple of naive questions, just to reconfirm. Call sample by trees, you're essentially masking features right within the tree, right?
Yes, I said, oh, because this is the missing COE member whose flight was cancelled yesterday evening.
And they lost my language, yeah.
And so you keep on winning. And it's exactly that, it's column sample by tree.
Okay.
And basically it says column sample by tree 1 is no masking. You get all the features for each of the trees.
And splits is the number of nodes in the tree.
Splits is the number of nodes in the tree, exactly.
Okay, thank you.
All right. Of course, I'm happy to take more questions and discussions during the breaks, but then thank you very much, and Joe, please take
Thank you.